Hi everyone. Welcome to the second video in Lecture 7 on differential geometry. In the last video, we talked a lot about manifolds and vectors, two concepts which are going to help us switch between different coordinate systems as we work on the state space in classical thermodynamics. In this video, we're finally going to actually get to those sorts of coordinate transformations that we'd like to be able to do. Okay, so without further ado, I've copied this manifold picture that we had from the last video. It depicts the state space gamma and a coordinate system on the state space, the A1, A2 coordinate system. Now here, we have the A1 coordinate system, or the A1 functions level sets in red, and the A2 functions level sets in blue. Let me now introduce a new good coordinate system. Remember that good coordinate systems are ones that specify every point of the system uniquely. So let's just do a couple of these. So I will do, here's 1, 2, 3. So let's say that this is the coordinate system B1, B2, and this can be B1 is equal to -2, B1 equals -1, and B1 equals 0. And then let's grab another color. Purple's probably good. Okay, so there we go. This can be B2 is equal to 1, B2 equals 2, and B2 equals 3. So whereas this point X in the A1, A2 coordinate system was equal to, let's see, so we had A1 is equal to 1, A2 is equal to 0, so it was equal to the point 1, 0. In this new coordinate system, B1, B2, X is equal to, well, we have B1 is equal to -1, and B2 is equal to 2. Good. And by design, this is going to be another good coordinate system, so we'll have no problems there. Now, I think that being able to convert between these two coordinate systems is something that should be relatively familiar. What we would need the functions a1 and a2, which we're now going to think of as functions in terms of b1 and b2. And on the other side, we need b1 and b2 thought of now as functions in terms of a1 and e2. And for any set of two good coordinate systems, these functions will all exist. So there will be invertibility basically between the two. And I won't get into that too completely because it should follow relatively easily. Once you sort of write A1 and A2, for instance, in terms of B1 and B2, you should be able to invert to get B1 and B2 in terms of A1 and A2. And as physics students, you will have had some experience with this. So I don't want to get into it too much more than I already have. What we do definitely need to talk about is how to change between these vector bases, vector space bases. So the next question is how to convert between basis elements. So let's go ahead and write or draw the basis elements for this new coordinate system. So first of all, we have the partial b1 vector, which points something like in this direction. Yes, that is the increasing direction. Good. And then we have the partial B2 vector. And I'll leave off the labels just to save us a little bit of space here. Okay, good. And let's just sort of blow up that picture really quickly. So we have our point X, and we have the B1 vector, partial B A1 vector. We have the partial A2 vector. We have the partial B1 vector. Make sure that I'm getting this all right. Yep. And finally, we have the partial B2 vector. And you've already probably done this in some linear algebra class, converted from the one set of vectors to the other. What we would typically do is create a vector of the basis vectors. So we would say something like partial A1, partial A2 on the right side, multiplied by some matrix are going to be equal to partial B1, partial B2. And the entries of this 2 by 2 matrix, you could go ahead and find if you knew the components of B1, I should say the components of the partial B1 vector in terms of the two partial A vectors, and the components of the partial B2 vector in terms of the two partial A vectors. So what we need, components of, let's say, partial BK in terms of partial AJ. All right. So let me just give you the rule. Partial BK is going to be equal to partial BK of AJ, partial AJ, where this implies a sum over J. This is, again, that Einstein summation notation that we introduced in the last video. And it should be noted that this equality is basically the chain rule, the multivariable chain rule. Because again, here we're thinking of this partial as being a real partial derivative in the BK direction of the function AJ, which we're now thinking of as a function of B1 and B2. All right, so this gives us everything we need in order to convert between these basis vectors. Good. Now, I think that it's a good time to introduce a second notation. And you'll see this all over the literature on thermal physics, and so I think it's very important for us to introduce it. Sometimes we'll introduce, so suppose that we have a three-dimensional state space, gamma, and functions A, B, C, X, Y, Z, why not? Such that any choice of three functions forms a good coordinate system. Then rather than coming up with the A1, A2, A3 coordinate system, the B1, B2, B3 coordinate system, and then naming all of those, sometimes it's helpful to just work with this ABC, XYZ by itself. So then we might use the following notation. We could talk about the partial of X while fixing Y and Z. So these are just examples. We could talk about the partial of X while fixing A and B. We could talk about the partial of A while fixing B and Z, or whatever else we wanted. We can choose any one partial while fixing any two other coordinates, and that will always be a well-defined object. Now, this corresponds to choosing, basically a new coordinate system every time. So, we could have the A coordinate system is XYZ, the B coordinate system is XAB, the C coordinate system is ABZ, but the number of different possible coordinate systems, if we have 6 functions, is very large, and so it can be just more notationally convenient to represent things in this way. And we'll see that we get some useful mileage out of this. All right. There are a couple more things that we need to get to go over before we're able to finish the video. All right. Now I think we've covered enough in order to do a good example. And this is going to be an example in which we're going to try to convert vectors between two coordinate systems. All right, so what should our coordinate systems be? So we'll have the xy coordinate system and the uv coordinate system. And what we're going to be given is that u is equal to x squared plus y, and v is equal to y. And our goal is to find partial u and partial v in terms of partial x and partial y. And let's be even more clear. This is partial u fixing v, partial v fixing u, partial x fixing y, and partial y fixing x. Good. All right, so let's get things written out. Let's do partial u first, just so that we get our footing. So partial u of v is equal to, well, partial u of x fixing v times partial x fixing y plus partial of y, of u fixing v times partial y fixing x. Good. Now, notice that this is exactly the same as what we wrote way above here, up here. If we convert to this new notation. Good. Okay, so what we need in order to do this is to actually have the functions x and y in terms of u and v. So need x of uv, y of uv. Okay, so let's invert the relations that we had above. It's not terribly hard to do so. What we get is that x is equal to the square root of u minus v, and y is equal to v. All right, so now we can find this red thing and this blue thing. Okay, so for the red thing, partial ux of v is going to be equal to, well, we get like a 1/2 u minus v to the minus 1/2, or in other words, 1/2 square root u minus v. Good. And for the blue thing, well, y doesn't depend on u in this new coordinate system. So partial u of y fixing v is equal to 0. And in particular, or I suppose I should say, when we want to find partial v fixing u, we're going to actually need the other two derivatives. So let's go ahead and figure those out too. So we have partial v of x fixing u. It's actually just going to be the negative of what we found before because we have this negative sign here. So it's minus 1/2 square root u minus v. And yeah, no, we're good. And then partial v of y when fixing u is just going to be 1. since y is equal to v. Very good. So now we're in a position to write both of these. So partial u fixing v will be equal to, well, sticking in these two derivatives, one of them is 0. So we actually just get this, 1 over 2 root u minus v times partial x fixing y, as here. And on the other hand, partial v fixing u, well, that will be equal to minus 1 over 2 root u minus v, partial x fixing y, plus 1 times partial y fixing x. Okay. Now, because we have this side in terms of partials of x fixing y and y fixing x, it would be typical to also convert the component functions into x, y coordinates. So let's do that as well. So to do that, we need to go back here. So look, x is square root u minus v. So we'll have an x in the denominator here and an x in the denominator here as well. So this is also equal to, let's write this correctly, 1 over 2x, partial x fixing y. And this is also equal to minus 1 over 2x, partial x fixing y, plus partial y fixing x. Now is a good time to talk about another way to see whether or not something is a good coordinate system. If you convert from a known good coordinate system to a new coordinate system, and the basis vectors are always linearly independent, then you have a new good coordinate system. So I'm going to note, maybe here, these are always linearly independent, which is not too hard to see because we have the same vector except negated for this first component, and then we have a second component. So I'll allow you to go ahead and prove that that means that they are always linearly independent. Okay, wonderful. So I think we're mostly good here, but I did want to point out one more thing, which is that notice that even though y is equal to v, the partial of v fixing u is not equal to the partial of y fixing x. So, if we were to think of this naively, y equals v, so partial of v equals partial of y. But that is not true. And it's precisely because of what is being fixed. In the first case, it's u, and in the second case, it's x. So we pick up that second term here. Good. All right, one last sort of set of things that I want to do in this video is talk about calculus identities. These are super important to our ability to work with this kind of stuff. And so I think it's very worth it to spend a little bit of time stating calculus identities in this new language, even though I'm not going to prove them here. The first thing I'd like to do is state the chain rule. Note that I already used the chain rule above in a certain sense, so this is just going to be a recap. There are two ways that we can use the chain rule in this differential geometric notation or formalism. The first is the one that we've seen before. So the partial aj is equal to partial aj of bk, partial bk. Now this is in the case where we have these two coordinate systems which are sort of complete. So k here runs from 1 to n, and j runs from 1 to n as well. Or I should say j could be any of the values 1 to n. But in the other notation, we actually have a nicer, or maybe not nicer, but a different instantiation of the chain rule, which is to say that, for instance, the partial of x when fixing y is equal to the partial sub x of z fixing y, partial z also fixing y. Okay, so how do we get this second one? The answer is that we need to use the first one in order to derive it, but the second one will be very handy on its own. So let me do that really quickly. So we'll need two coordinate systems. The first one will be AJ, or maybe I'll just say A1, A2 is equal to X, Y. And the second one, B1, B2, will be equal to Z, Y. Good. Okay, so now let's write the chain rule, this chain rule, and I'll do it in red just to indicate the difference, in terms of what we have written on the right. Okay, so the partial AJ, well, there are two possibilities here, but we're interested in partial A1, since A1 is equal to X. So partial of A1 when fixing A2, and in this notation, we don't really need to write that fixing thing, is going to be equal to the partial A1 of B1 times the partial of B1 plus partial A1 of B2 partial of B2. But now let's write this in terms of what we want. So this is the partial of X when fixing Y, since that's the A coordinate system. This is going to be the partial of X, the partial with respect to X of B1, but B1 is Z, fixing Y again, times the partial of B1 when fixing B2. So that is the partial with respect to B1, which is Z, fixing B2, which is Y. Okay, then for the second term, we get the partial with respect to A1, which is X, of B2, which is Y, when fixing A2. But A2 is also Y. And then this is going to be times the partial of Y, sub Y, when fixing Z. But look, if we think about the partial of Y with respect to X, when fixing Y, then Y is a constant. So this term must be 0, and we're left with exactly the identity that we want. Good. The second thing that I'd like to point out is how we write the inverse function rule in this new notation. And this is not actually going to be too extensive. So it's just that the partial with respect to X of Y fixing Z is equal to the inverse of the partial with respect to Y of X when fixing Z. Good. And this here means the multiplicative inverse. Okay, one last identity that we're going to need is the so-called triple product rule. And this is one that you probably haven't seen before, but is very useful in a number of situations in thermal physics. And it goes like this. Suppose that we have X, Y, Z, W such that any three are a good coordinate system. Then partial X of Y when fixing Z and W times the partial Y of Z fixing X and W times the partial Z of X fixing Y and W is equal to -1. A couple of things to point out here. W is actually a stand-in here for arbitrarily many other coordinates, all of which are fixed in all three factors here. Then I want to point out that there's a sort of cyclic nature to what's going on. So if we always underline the X in, let's get rid of these red underlines under the W. If we always underline X in blue, underline Y in green, and underline Z in red, then we always have blue, green, red, where then we cycle, and so blue would shift all the way to the right as everything else moves to the left. So we have blue, green, red, blue, green, red, blue, green, red. So we have sort of cyclic permutations of these three variables, and these are equal to -1. We'll see how this, combined with the inverse function rule, actually allows us to do a number of useful manipulations in some future lectures. But for now, I'll say thank you so much for watching the video, and I'll see you in the next one. Bye-bye.